Okay, I'm just going to go back through these notes and expand on a couple of points that I didn't really hit on all that well. And then there's a little bit of new material that'll be presented, and then I'll kind of work through an example that highlights these things. And my dog's gnawing on a bone behind me, so sorry for that noise. But yeah, this first page is kind of the general layout. This is all good. There's nothing here that's really missing or anything of that nature. Um, and all of this is correct. But the one thing that I'll kind of highlight here is in my summation of moments, I've got summation of moments about G is equal to the inertial term IG alpha, and that is it. That's the only inertial term that you're going to have when you are summing moments about the center of gravity. Because if I look at my inertial components, which are alpha, AY, and AX in this case, AY and AX, as I've drawn them, they go through the CG. So those cannot create inertial moments. So the only thing left is IG alpha. So that's why that one looks like that. For translations, by the same logic, there is no rotation, so you don't have an alpha term. And through the CG, even if you have an acceleration, it's going through the CG when you only have a translation. So that's also not going to create any moment. And then that form right there should be perfectly fine. If you are not summing moments at the CG, that does not work. In that case, you are going to have to factor in inertial moments. That kind of shows up in this little homework problem here already. You're summing moments about A or B. Those are not the CG. CG's somewhere in there, but those aren't it. So this mass times acceleration that you calculate from the rotation, it's not at the CG, so it is creating a moment, and it must be factored in. That's the big note there, is that this equation, the boxed equation, as it's written, is correct because it's about the CG. But if I take into account just some other point on the object, let's just go over here. Well, now, if we're in an XY frame, I've got a distance up to that point in both the X and Y directions. So that A term right there, that'll have X component and a Y component. And now when I take the summation of moments, you're going to have inertial terms. So in that case, my summation of moments at P is not equal to 0. It's equal to, in this case, we'd have the mass times AX times, well, it's actually going to be this distance here, which is the Y, effectively. Let's give it a direction of clockwise positive, and then we'll have mass times a Y, and its offset distance is going to be the X component there. All right, so you got to include both of those. And even in kind of getting all over the place here, but in problem 3, when we're back to this, you've got two different inertial terms, one for the original weight, but then this little connecting rod also has an initial term, which is different. So you'll have, because its action of radius there is different, the acceleration is different. So in that problem, you do have two inertial terms that come into it because of that. So this kind of logic, if we were to come down somewhere and just take a summation of forces, the summation of forces don't change. Those are still going to be based upon accelerations at the center of gravity of the object, but the summation of moments, so I could kind of add a fourth equation to that set, or that set, that do say the summation of moment at P is equal to summation of inertial moments And the terminology, the textbook I mostly work out of uses something, I don't even know what that is. It's like a script M or some Greek letter or something to that effect. But what that letter is those those inertial moments. So those would be the mass times acceleration times the offset from the point where you're summing moments, basically. So we worked some examples like this, but I never really laid out the equation for it. So that's one of the things I wanted to cover here. And then in rotations, that what we just looked at kind of has some application here as well that needs to be covered. So again, this is what I gave you yesterday in the video, but there's nothing wrong with these equations as they're set up, but they are specifically set up about the CG of the object. So the same kind of logic applies. And for pure rotations, we can also say that a summation of moments at the center of rotation is equal to the moment of inertia based at the center of rotation times alpha. Just purely that. There's no other summation of moment terms necessary in that. So this is valid for rotations. Well, they're valid for fixed axis rotations. About O, which is the axis of rotation. Okay, and then just kind of a quick little explanation of that. If I was to sum moments at O, inertial moments in this case, so I guess that should be the little cursive script. The normal component passes through point O, so it doesn't create a moment, but the tangential component, mass times AGT, is at, from my diagram above, RG, distance RG. And then I would still have the IG alpha term. Remember, IG alpha is an inertial moment, and that's just like in summing moments in statics. If you've got an applied moment to a body, it doesn't matter where it's applied, it just adds into the summation of moments. That's the same kind of deal here, so I can still include that because it's just an applied moment. When I do that, and I factor in the fact that AGT is just equal to RG alpha, that's a little bit of kinematics. And then rewrite my summation of moments, factor the alpha out, mgr squared plus IG, well, that would be equal to, by the parallel axis theorem, the moment of inertia about O. That's just the definition. It's literally the definition of the parallel axis theorem. So because of that, we can say that for pure rotation, that initial form, summation of moments at O is equal to IO alpha, is still correct. So no real issues on this page. I just wanted to make sure to highlight why that is accurate. And then on to general planar motion. Now here there is a little bit extra work necessary. What's shown is okay because, again, I'm at the CG for my summation of moments. But when I move off of that, then I do have to include additional terms. So essentially, and we'll just, I kind of already did this on the first page, but we'll do it one more time here. If I've got some other point in the body that I want to sum moments about, we'll just call that P, then we've got one more expression that's necessary. And here it's actually summation of moments at P is equal to the summation of the inertial moments. And then that's it. IG alpha is one of those inertial moments. So sometimes you'll see it written like this separately, but whether you see it or not, it would kind of fall into that definition. But I'll leave it like that because I think that's a little bit more descriptive. So the summation here, those are going to be your moment components, or I'm sorry, your components of accelerations written out. So kind of expanding that just a little bit. We've got same kind of deal. We've got P is offset from where my acceleration is. The acceleration will have X and Y components. You're going to have those offset values, which I'll just again call them capital X and capital Y. Those are distances, position distances. And then so here we would have mass. I could just use brackets here. AX times the perpendicular distance, which is Y, capital Y, plus, and let's see, you'll go clockwise positive, which makes AXY actually negative. AXY is positive. AYX would be causing counterclockwise rotation. And then plus IG alpha, which I think back here I might have had, yeah, it'd be the same thing here. The AX component would be positive, but the AY component would be negative, so that little guy should be negative. And that's essentially the difference. That's what I was leaving out, is that when you're summing moments at some location other than the center of gravity, you do have to take into account those inertial moments that are created by your linear accelerations. In terms of examples, the ones that I did in the video, those were all about the CG, so there was nothing different there. Those were all fine. The ones I did in class today, those are not at the CG, which is why they looked a little different, and there was a little bit of additional work involved with them. But I just want to do real quick, if all that made sense, this example probably ain't going to be any extra use to you, but if there's any additional kind of questions, maybe this will help a little bit. So let me draw in, and this is going to be pretty much your one of your homework questions, or close to it. It's not going to be fully solved, but a big part of it. So this is our sphere rolling down a inclined plane, and I'm just going to solve all this symbolically. Theta, yeah, that's pretty much it. So this is asking for the time it takes to travel a certain distance. For that, you're going to need the acceleration, and then from there, it's a little bit of a kinematic problem. But getting the acceleration is definitely a kinetic work. So in this sphere, if I have my center of gravity G, and then I've got a point of contact that I'll call O, and I'm going to have the weight. I'm going to have a normal force. I'm going to have, it's going to be rolling down a curve. We're going to have term I alpha. It's of some radius. It's called capital R. And we've got our inertial term acting through the CG of, well, we'll call it just MAX. And there is one more force that's necessary here, and that's if this is not slipping as it rolls, there has to be some essentially friction between the sphere and the plane. If there's no friction, it would just slide down the ramp. It wouldn't roll without slipping, as the well, as problem 4 on your homework states at least. So we'll do the same thing here. What that means is you got to have some force of friction acting up the ramp to keep it from slipping. Now, I don't have any information in the problem statement or in this little setup to solve for that f of f initially, but it has to be there, or else the thing's not going to be able to rotate. So now to solve this, I'm going to give my coordinate system as x along the direction of travel and then y vertical. And I know I've got 3 equations I can write directly. Sum of forces in x is equal to max. Sum of forces in y is equal to may. And for now, I'm just going to write sum of moments at g is equal to ig alpha. Well, let's just go ahead and write it. We can also say that sum of moments at O is equal to And there we said we have a summation of the inertial moments plus G alpha. Okay. So forces in X, we're going to have that force of friction and a component of weight. That would be W sine theta is equal to MAX. And Y, which, by the way, the only equation that I need out of this is the summation of moments, but I'm just writing them all out for completeness, I guess. N minus W cosine theta. And it's not moving in the y direction that I've chosen, so that's equal to 0. And then summation of moments about G. Well, we've got the force of friction at distance r, and that's it. That's going to be equal to G alpha. Now, I don't know that force of friction. I don't know alpha. And from that first equation, I don't know AX. I can do some things there to solve that, but if I take a summation of moments about 0.0 instead, let's see what we get there. So now we've got the weight term, W sine theta times R. Do I have that going the right way? Yeah, because I'm taking both of these as clockwise positive. And then from the statement there, I'll put IG alpha first, plus mass times AX times R. Well, in that one, we've gotten rid of the force of friction, so that's not unknown anymore. But now alpha and AX are unknown, but that's okay because AX has to be equal to alpha times R. There's no, it's just a sphere rolling on a plane, and we've talked about that before. That relationship's always going to be true if it's rolling with no slip. So that lets you eliminate either alpha or AX, either one. And since ultimately the most useful thing in this in the homework problem is AX, you can just eliminate and solve for that. And that lets you proceed with the problem. Now it's worth one more little thing that is relevant here is that for any sphere or cylinder, or I guess those are the big ones, that's rolling with no slip, that point of contact, and we at least discussed this in passing, that point of contact essentially acts like an instant center. 0.0 acts as an instant center. And it kind of has to because it's not slipping, it's not sliding down the plane. So at any given point in time, the point of the sphere that's in contact is not moving down the ramp. It's just acting as kind of a fulcrum to rotate about. Because of that, we get one more little detail here. So if we sum moments at an instant center, it's going to be equal to the moment of inertia, if you can calculate it, at the instant center times alpha. Because going to the moment at the instant center, it does the exact same thing that we looked at back over here, that we looked at right here. Because the instant center literally acts like a point of rotation, just like it does in a fixed rotation problem. So similar kind of thing there. So that's one more fact that can be used to solve problems at times. I don't think that comes up as helpful in any of the homework solutions, to be fair, but you can do it. So in short, this little chunk right here is essentially everything that you need to solve that that fourth homework problem. There's nothing else that's really necessary. And then just coming back here, just keep that in mind for your general plane motion. If you can, some moments at the center of gravity, then you end up with just IG alpha as your only inertial term. If you can't, then you do have to include the components like so.